Alright, what's up everyone? Welcome back to Structure Free Learning. And in this video, we're going to talk about stress transformation using Mohr's circle. And hopefully by the end of this video, you'll be able to explain what Mohr's circle is and also understand the process of how to draw a Mohr's circle. But before we get started, let's consider the stress transformation equations that you probably covered already. These stress transformation equations were derived based on equilibrium of a plane stress element. And what they do is they describe how to go from one given state of stress into a new state of stress at a different orientation. And Otto Mohr, the German civil engineer, back in the late 1800s, he said, hey, let me look at these equations, and if I can manipulate them to get rid of theta, they look awful like an equation of a circle. And what Otto Mohr did was come up with a graphical technique to stress transformation for a given state of stress to a new orientation, especially during a time when a lot of calculators weren't around. But nowadays, you've got calculators, so it's not too hard to apply these stress transformation equations. But nonetheless, people like to still use Mohr's circle because it visualizes the problem that they're solving. When you want to draw Mohr's circle, a problem starts off by giving you a state of stress. And we're just going to deal with plane stress conditions here in this video. And normally you're given a state of stress that has numbers or stress values associated, but no specific definition. So given stress values to describe the normal and shear stresses, the first thing we want to do is establish a coordinate system. And this is our local coordinate system for the given plane stress element. And normally what's done is the horizontal is described as a plus x-axis, and the vertical is the plus y-axis. And this is important to establish or define our stresses, like what is sigma x, what is sigma y, what is tau xy. Now that you've established a coordinate system, you're ready to define stresses. And here it's really important to make sure you distinguish between a positive and negative stress based on your coordinate system. Here, this red arrow, this normal stress here in this horizontal direction, that's a positive sigma x because it's causing tension on this face. And then here, this vertical stress, this red arrow here, would be the plus sigma y because it's causing a tension stress on this face here. This red arrow here is a positive shear stress. And the reason that this is positive is because this red arrow is on the positive x face in the positive y direction. And the way I look at this is a positive times a positive makes it positive. So if I looked at this arrow here, this would be on the positive y face in the positive x direction, positive times positive. And it works if I go down here. If I look at this arrow down here, this is on the negative y face in the negative x direction. This would be a negative times a negative, which would be a positive number. What we've just done are part of the two most important things. The next thing that we want to do is establish a coordinate system for us to actually draw Mohr's circle. And depending on who you talk to or what textbook you reference, you're going to draw your plus sigma to the right, plus tau up, maybe plus tau down. I like to draw my sigma and tau axes, plus sigma to the right, positive towards the right, and my tau axes vertical with positive shear stress downwards. And the reason I like to do this is so that when I rotate a Mohr's circle counterclockwise or clockwise, it's the same as on the stress element. So if I rotate counterclockwise in Mohr's circle, then I'm going to rotate counterclockwise on my stress element. Next, we want to determine the center of Mohr's circle, which is located at sigma average, comma 0. Sigma average is the average of the normal stresses. And that point would be somewhere along the plus sigma axis because the tau value is 0. So this red dot will represent the center of a Mohr circle. I'll put a C on there. Next, I want to establish a point on the outer radius. And that location I'll call point A. And simply you can just use sigma x tau xy. And these are the stresses that you defined way up here earlier after you defined your coordinate system. If sigma x and tau xy are positive, that first point is going to be somewhere down over here. And this represents the point where theta equals 0 degrees, or how you have defined the origin, this plus x, the basic reference. Again, this line right here represents theta equals 0 degrees. Any sort of angle you're going to define from this location. This is your origin, if you will, for the angle. And once you've done that, you just, draw a line connecting the dots, then swing that line all the way around and make a circle. Now is a good time to look for something round, like the bottom of a cup, or actually buy a compass or something, right? It's like the one time you're actually going to use a compass. So I'm using a tape, like that thing of masking tape. Alright, that looks alright. Oh, I'm going to have to make point A look a little bit better. Sometimes I like to draw the circle first and then draw the axes and all that, just because of scale and everything, and it's harder to draw a good circle than draw anything else, as you can see. And now, after you've determined Mohr's circle, or you've drawn it, it's really just a whole graphical process to calculate everything else. So one of the first things that you can always do is calculate the radius of Mohr's circle, which is just this distance, or this arm right here. And that's not hard at all when you use the right triangle. So here, bam, and bam. And if you recall, this distance is sigma x minus sigma average. And this vertical distance is tau xy. So the radius is the square root of sigma x minus sigma average squared plus tau xy squared.